So the next video in Chapter 7 is on Newton's Law of Universal Gravity, which is in Chapter 7-3 of the textbook. Okay, so gravity, of course, you're all hopefully a little familiar with gravity and know that it's an attractive force. And it's attractive force between any two masses anywhere in the universe, actually. In the force of gravity, and if you think about this, this kind of makes sense because it's going to be proportional to the masses. So the bigger the mass is, the bigger the force of gravity is going to be. And it's indirectly proportional to the distance between them. So if you have masses that are close together, that's going to be a large force, but as you move the masses further apart, you're going to get smaller and smaller and smaller forces. Now, as it turns out, it's actually indirectly proportional to the square of the distance between the masses. So then you can actually write down Newton's law of universal gravitation that says that the gravitational force, F sub g, it's equal to, so we've got our two masses, m1 and m2, and the distance divided by the distance between them squared, and we need a constant of proportionality in here, and this constant we call capital G, which is known as the universal gravitation constant, or sometimes called Newton's constant, the value of which you actually have to go out and measure. We'll talk about that in just a second. But in SI units, the universal gravitation constant is 6.67 times 10 to the negative 11 Newton meters squared per kilogram squared. So one way to think about this, if you have two masses that are exactly 1 kilogram each, and you separate them by a distance of 1 meter, then you'll have a gravitational force between them of 6.67 times 10 to the negative 11 newtons. So gravity, as it turns out, is a very, very small, a very weak force, which is actually not surprising, right? If you have two 1 kilogram masses, you don't notice the gravitational attraction between them because it's so small. You need very, very large objects like the Earth or the Moon to actually have a noticeable force of gravity. Now, and just one comment here, of course, Newton is famous for this, and you may have heard a story, something about Newton is out in an orchard and he sees an apple fall and he has this, epiphany about gravity. And of course, the thing that Newton realized was not that apples fall. I think people from, cavemen probably realized that apples fell. But the important thing, and that's actually kind of illustrated in the picture here, so there's an apple and there's the moon. So actually the important thing that Newton realized is that it was the exact same force of gravity that caused apples to fall if you're on the surface of the Earth, and it's the exact same force of gravity that causes the moon to revolve around the Earth. So they're exactly the same force, and that's why this is called the universal law of gravitation, because it's the same gravity everywhere in the universe, from the surface of the Earth to the planets to the galaxies to the whole universe. Okay, oh, and just one other comment here. So this distance r, this is a subtle point, but can be important. So r is measured, so if you have spherical objects, like the Earth and the Moon, which are nearly spherical, this distance r is measured from the center of one object to the center of the other object. And the direction, of course, is always attractive. That's actually one of the things that makes gravity interesting, because it's always an attractive force. So that's actually why, if you look at very large scales in the universe, it's actually gravity, although it's very weak. Gravity is the dominant force, because it's always attractive. So if you have little bits of mass, they tend to be attracted to each other, so they tend to clump up together and build bigger bits of mass and bigger bits of mass and bigger bits of mass until you end up with things like stars and planets and whatnot. Okay, just a little side note here. So we mentioned in the previous slide, right, we had this constant capital G, the universal gravitation constant. So this is something you actually have to go out and measure. So when it was actually Cavendish was the first guy who measured this. It's called the Cavendish experiment. And experimentally, I just find this kind of interesting because, well, we already said that gravity is a very, very weak force, so it's a very challenging experiment to do. And so, in fact, the way it's kind of interesting how he did it, he used something called a torsion pendulum. So for the torsion pendulum, so you have these two masses that are mounted on a little string, and it can rotate. right? So you imagine this little crossbar here on this little wire, and it's actually able to rotate. Then you take these two larger masses, you move them closer to the smaller masses, so you get a gravitational attraction, and it's tiny, but you expect the torsion pendulum to tilt just a little bit. So, and again, it's kind of interesting, the torsion pendulum actually allows you to take this really teeny tiny angular displacement, and then if you shine a light, or if you just make this thing really, really long, you can actually turn that into a fairly large linear displacement, and it's something you can actually measure. And the value Cavendish got for G, for capital G, is actually pretty close to the accepted value today. Okay, and so this law of universal gravitation we can also write in vector form. So I'm doing that here. So if you want to know the force of object 1 due to object 2, well, it's the same capital G, m1, m2 over r squared, and r hat is now our unit vector, right, pointing between object 1 and object 2, right? In the negatives, we put the negative sign here to make sure that we get an attractive force. And also just a little side note, so if you compare the force of object 1 due to object 2 to the force on object 2 due to object 1, and essentially you're just exchanging 1s and 2s, and actually the r hat vector changes. So the force of object 1 on 2 is equal and opposite to the force of object 2 on object 1, which it had to be the case from Newton's third law. Okay. And so r hat is our unit vector. And yes, so the other important thing, right, so this is just if you have 2 objects. But what if you have 3 objects or 4 objects or 27 objects? Well, what you can do, you apply something called superposition. And if you have a whole bunch of different masses at different spots, and if you want to know what's the net force on one of those in particular, all you need to do is take the vector sum of the forces from each individual object. So if you have one object that you're interested in and 3 different objects spread around, you just find the forces individually from each of those 3 objects, do the vector sum, and that'll get you the net force. Okay, so gravitational and inertial mass, this is kind of an interesting point. So we said gravity is an attractive force between any 2 massive objects, and the strength of gravity, right, is controlled by the mass. So the bigger the mass, the larger the force of gravity. So you could think of the mass that shows up in Newton's law of universal gravitation as the gravitational mass. Now, we've also encountered mass before, right? So mass showed up in Newton's second law of motion. The net force is equal to the mass times the acceleration. And the mass here was actually the measure of the inertia of the object. How hard is it to change the motion? So you can think of this as the inertial mass. So it's kind of an interesting accident. Well, perhaps not an accident, but it's interesting that actually the inertial mass and the gravitational mass are exactly the same thing. So in fact, this is why, right, and we talked about with free fall, so in the absence of air resistance, all objects fall at exactly the same rate. And the reason why they do that is because the inertial mass and the gravitational mass are exactly the same. If they were different, that wouldn't actually happen. Now, this may seem like a simple thing, but it's actually not, and it's actually telling you something very fundamental about the nature of how the universe works. And in fact, this is one of the key points that actually led Einstein to develop his theory of general relativity. So general relativity is actually a more complete theory of gravity than Newton's law of universal gravitation. And we're not going to talk about general relativity because the math you need to do general relativity is actually pretty hairy. But basically what general relativity says is that you can think of gravity as a distortion of space-time. So mass causes these distortions of space-time, which causes objects that travel near the masses to actually get bent, right? So that's one way you could think of gravity arising. It's actually this curvature of space and time. And one of the predictions from general relativity is actually that even light will actually get bent near very, very large masses, which if Newton's law of universal gravitation was all there was, well, light doesn't have any mass, so it shouldn't be affected by gravity. But in fact, observations have shown that in fact, light is bent by very large masses, so it's actually general. So this is one of the first first pieces of evidence supporting general relativity.